Well, welcome to Physics Lab in the time of the coronavirus scare. So, I've been thinking about how we could proceed with doing our labs, which are on-campus labs, when everybody has been told not to come to campus. And although it is possible that we could be back on April 6th, and in fact should be back on April 6th, it is also entirely possible that we won't be back on April 6th. So we have 3 more labs this semester. We would have 3 weeks to do them in if we in fact do return on April 6th. But I don't think that's going to happen necessarily. I can't guarantee that it will happen. And we need to have at least 2 more labs to have had a full semester. Usually we do 10 labs in a semester. This semester we happen to have had 11. So the solution that I've come up with for what we would have done this week is that I'm going to film myself basically doing the lab but without any special commentary. And you can record the data from the film, and that is how you will basically do this week's lab report. Now there's a separate video already out there in which I discuss what you're supposed to do in the lab. Briefly, what you are doing in this lab is using a galvanometer to build a voltmeter. And the way that that works is you have a galvanometer which has full-scale deflection at, I want to say, 500 microns. And then in addition to that, you have a pair of resistors, and you need to have some power supply with a reliable DC voltage output. All right, step 1 is that we need to hook up the first resistor to the galvanometer. And then we hook up the pair in series, and we hook them up then to our DC supply, which I'll show in a minute. And that DC supply will put out 3 volts, and we want full-scale deflection, 500 microamps on the galvanometer at 3 volts output from the power supply. Now, the galvanometer that I have is marked from -50 to +50. The units, therefore, are times 10 microamps. So at 50, it really means 50 microamps. We want 50 microamps on the galvanometer when the voltage is 3 volts across the resistor and galvanometer combined. All right, that'll be step 1. Step 2, I will tell you after we have done step 1 and after you see what the experimental setup is. All right, this computer, which is sort of the brain of the operation in a sense. It is set up so that it is putting out a DC voltage. So I've set up the waveform to be DC. I have 3 volts. Zoom in a little bit and see here. You can kind of read that. Well, you'll have to trust me if you can't make out that it says 3 volts, that this is a 3 volt output. And then I have set up, and you don't have to trust me so much on this one because you can see it with your own eyes, 2 digital displays. The top one is the voltage as measured by a voltage sensor. So let's look down here and see what's actually plugged in to our box. So this right here is the voltage sensor. If we follow it along, branches, and you can see that one end of the branch plugs in here to our galvanometer. The other end of the branch, so here's the branch, so the other end plugs in here to our resistor box. Alright, then in addition to that, there we go, we have a pair of wires that are coming out of the universal interface. Wire 1, wire 2. And they come to here. And then if I trace along them the rest of the way, so it would be nice to have one other person to run the camera. But, you know, you have to be in a state of panic. So one wire goes here, the other wire goes here, and then we have a wire connecting from here to here. So these two are in series. Alright, and what I'm going to do is I'm going to turn on the computer. This will get us a voltage output. So now there's some voltage. It is just shy of 3 volts. It's close enough. And what I need to do is I need to come to my resistor box and to my ammeter and see what the resistor box says and see what the ammeter is. So first of all, the ammeter, you see that the dial is beyond 50. So here's our dial. And you see that currently the resistor box setting 0, 0, 0, 0, 0, 0. So it's set to 0. And what we're going to do is I'm going to turn these dials, and you need to see when is the deflection, right at the 50. So I will start with turning the big dial, the times 100K dial. So 100K is too much. This is the 10K dial. I just turned it to 1. So this is the 1K dial. This is 1. 2, 3, 4, 5, 6. Alright, so here's 6, here's 5. Now I will also go to the lower dials. I'm not necessarily going to just stop when I get to the right answer, by the way. So this is the 100 dial. 1, 2, 3, 4, 5. Just a little. 6, 7, 8, 9. Alright. 10. ones place, I think we have to zoom out a little so we can, or the tens place, we have to zoom out a little bit so you can see both it and the dial. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And just for good measure, I'll turn this one to 8 and I'll repeat. So this is 5,800, 5,810, 20, 30, 40, 50, 60, 70, 80, 90, this would be 5,900. Okay, so now I'm going to reset to 5,900, 5,910, 20, 30, 40, 50, 60, 70, 80, 90, and this would be 6,000 that we are at now. Okay, and so let's go up here and check with 6,000. So this is now 5,000 even. And this just, oops, a little bit. Pointing to the 5,000. The state of the dial is this. Point it to 6,000. The state of the dial is now this. 7,000. Okay. 6,000, 5,000, 4,000. Alright, so we've done 5,000 and lots of increments in the hundreds. Let's do 6,000 and some increments in the hundreds. So here's 6,000 even, 6,100, 6,200, 6,300, 6,400, 6,500. Returning to 6,000, 6,010, 6,020, 6,030, 6,040, 6,050, 6,060, 6,070, 6,080, 6,090, 6,100. Back to 6,000. Okay. So in all that data, you have enough to do step 1. So now let's reset the camera. Alright, here's the relevant diagram and what you're trying to figure out for this first step. Call this step 1 if you'd like. What you're doing is you are determining the value of the resistance R1 that gives full-scale deflection for the galvanometer in this setup with a 3 volt voltage drop across the pair. And you're determining both the resistance and the uncertainty. So if the resistance that, let's say you're looking and there seem to be a range of resistances. Maybe the range is from 4,000 ohms to, I don't know, 4,100 ohms. So if, for example, that range of resistances for R1 all appeared equally to give the same full-scale deflection, you can't distinguish, then you'd say something like R1 is in the middle of that range, so 4,050, and the uncertainty is this sort of like the size of that range. So from 4,000 to 450 is 50. From 4,050 to 4,100 is another 50. So the uncertainty here would be 50 ohms. So in your lab report, you need to write these two numbers down. So now let's look at what step 2 is going to require of you. In step 2, we are attempting to determine the internal resistance of the galvanometer. The way that we're going to do that is we're going to hook up another resistor. We're going to leave the first resistor in place. We're going to hook up another resistor, and this new resistor is going to give us the internal resistance of the galvanometer by being hooked up in parallel to the galvanometer, but in series with the first resistor, R1. So we'll call this new resistor R2. All right, and what we're going to do is we're going to adjust the resistance of R2 until our galvanometer deflection goes from full scale to half scale. So full scale was 500 microamps. Half scale will be 250 microamps, but that's the 25 on the galvanometer that we have here. All right, so let's go ahead and hook these up in parallel. We're going to not touch resistor R1, by the way. We don't want to change the resistance value of R1. It's already correctly calibrated. All right, for what it's worth, this is the diagram for step 2. What we are determining here is the internal resistance R2. And again, there could be an uncertainty and a sort of middle value for the internal resistance. We are leaving resistor R1 alone. We are adjusting R2. When you have a half-scale deflection, R2 is equal to the value of the internal resistance of this galvanometer. And zoom out. This right here is resistor R2. We're leaving it alone. R1, excuse me, this is R1. This is our galvanometer, again, and this is resistor R2. And currently, resistor R2 is set to the zeros. So 0, 0, 0, 0, 0, 0. And of course, that means that the galvanometer, as expected, has a total current of 0 because all the current is going through this resistor, which is in parallel. Okay, so let's key in on the galvanometer again. And what we're looking for is the resistance value such that we get half-scale deflection, which is the 25 here means 250. Okay, so what I'm going to do here is I'm going to adjust dials on this guy. I'll start with the hundreds dial, and I'll just read off the value that I'm using for the resistance for each case. And you just write down what you think is the right answer. Okay, so the hundreds is this one. I've just turned it to 100. Here's 200. Here's 300. Here's 400. Here's 500. Here's 600. 700. 800. 900. And 1,000. All right, so let's go back to 0 case, and we'll do by 10s there, and then we'll do by 1s, and then I'll repeat in the 100 case. Okay, so zeros, here is 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. Okay? So, now let's repeat that for the 100s case. So here's 100, 110, 120, 130, 140, 150, 160, 170, 180, 190, 200. All right, let's zoom in a bit on this. And what we want to do is we want to set dials around so that they are, roughly correct. So I've set to the correct hundreds place value. And right now I am going to go to the 30s of that hundreds value. So you've got to have written down the correct hundreds place, whether it's a 0, a 1, a 2, etc. And right now I've got it on 30. Okay? So 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. Right, so now I'm going to reset to 40. So this could be 40, it could be 140, it could be 240. You've written down the correct hundreds place. So 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50. Okay, so now let's go ahead and reset it, and we'll go to the 50s place. 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60. Now we reset. We start from 60 and by ones. 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70. All right, so you need to have determined what value to hundreds place, tens place, ones place. What value is the approximate average value at which this had a half-scale deflection? And what is the uncertainty based on these measurements? Okay. For step 3, what we're going to do is remove resistor R2, because now we know what the value of the internal resistance of the galvanometer is. And what we're going to do is we're going to predict what is the actual value of R1 that we would have to change R1 to. We could call it R1 prime if you'd like, or R1 new, or R1 sub 8, or something like that, such that now our voltmeter goes from 0 to 8 volts. So in other words, at 8 volts, we are at 500 microamps on the galvanometer. We're going to change R1. We're going to remove R2. All right? And so you should calculate this using basically the equations that are in your handout and in the other video that I made. You should calculate what value you need to set R1 to in order to make this happen. All right? And now I'm going to repeat adjusting the value of R1, excuse me. And you're going to write down the value at which this actually happens. And you're going to write down the uncertainty, and you're going to ask, is your calculated value within the bounds of the uncertainty or not? And you're going to ask, what is the percent error if it is outside the bounds? All right? So step 3 let's look at the board and see what step 3 diagram now looks like. Alright, so first of all, do we faithfully have 8 volts coming out of the computer? Yes, within a reasonable margin of error, less than 0.5%. So now what we do is we repeat this full-scale deflection thing. Okay, so I'm going to again focus on the galvanometer. Okay, so what is the full-scale deflection unit? Alright, so I'm going to set this galvanometer, this resistor, just to 0. And I'm going to start with the 10,000s. And I'm going to start clicking the 10,000s up. Okay, so right now we're at 0. Here is 10,000. Here's 20,000. Here's 30,000. Just a hair. Okay, so this is 30,000, 40,000, 50,000, 60,000, 70,000, 80,000, 90,000, 100,000. Alright, so now I'm going to reset the galvanometer. I've set it to the correct digit in the 10,000s place, and now I'm going to change the 1,000s place. So this is something times 10,000 plus 0. And here's plus 1,000, 2,000, 3,000, 4,000, 5,000, 6,000, 7,000, 8,000, 9,000, 10,000. So if your correct thing in the 10,000s place was a 20,000, then this right here is now 30,000. The 9,000 would be 29,000. If it was 10,000, then this is 20,000. The 9,000 would have been 19,000, etc. Okay, so now I'm going to set it to the correct value in the thousands place. And now what we're going to do is do the hundreds place. Trying to reduce glare a little bit here. It's kind of a losing battle on this camera, unfortunately. Alright, so it's got the correct 10,000 place, it's got the correct 1,000 place. Let's do the hundreds. This is 0, 100, 200, 300, 400, 500, 600, 700, 800, 900. This is 1,000. So let's see if I rotate the camera, whether you can actually see better where the needle is pointing. It's a little better angle on it. So I'll repeat from this angle. So 0, 100, 200, 300, 400, 500, 600, 700, 800, 900, 1,000. Alright, so I'm only going to ask you to get to this nearest 100. I will not do any further with the 10s and the 1s. Alright, we are ready to proceed to the fourth part of this lab. This part of the lab was not originally part of the lab on campus. We added it this semester. It's not discussed in my other video, but it's kind of a completion of this lab. The lab felt incomplete without it. Basically, what is happening is we've built for ourselves a voltmeter. We've calibrated it so that it can have a full-scale deflection at 3 volts. We've calibrated it so it can have a full-scale deflection at 8 volts. Currently, it's calibrated to have a full-scale deflection at 8 volts. So what I'm going to do is I'm going to take a pair of resistors, and they do have known resistance. I'm going to put them in series with each other. We'll call these resistors R3 and R4. I'm going to plug the pair of resistors into the power supply. That way we have 8 volts across the pair of them. And what I want to do is take the voltmeter that I have constructed and see if we can measure the voltage drop across each of the 2 resistors. All right, here is the setup of step 4. What we have is an 8-volt power supply connected in series to a pair of resistors marked R3, which is 3,000 ohms, and R4, which is 1,000 ohms. And what we want to determine on this step is the voltage drop across R3, which we're calling delta V3, and the voltage drop across R4, which we're calling delta V4. And what we're going to do in order to accomplish that is we're going to hook up the voltmeter across each of these 2 resistors in sequence. So right now it's shown hooked up across R3, then we move it to hook it up across R4. So let's see how that's accomplished. Let's make sure that we actually have the 8 volts output. And yep, it's 8 volts output and it's running. So now we come over here and we look at our 2 special resistors that we've set up. So this one would be R3. If you look very closely and carefully, you might be able to read or might not be able to read that it's 3,000. This one is 1,000. This is R4. Okay, so what I'm going to do is I'm going to take R3 and I'm going to hook up my voltmeter across it in parallel. Straight. So I come over here and I look and I see where the needle is on the galvanometer. And that tells me what the voltage drop should be for resistor R3. So you've got to convert this current into a voltage based on what you've done so far. And now I'm going to go ahead and put it across the other resistor. So here it is across resistor R1. So convert this into a voltage. Alright, so if I disconnect it and if I reconnect it, and that gives you some idea of the scale that we're on. Disconnect, reconnect. Okay, so this is R4 and therefore delta V4. And once again, if you want to see it once again, R3 and therefore delta V3. So I've connected it. Now let's disconnect it. Reconnect it. Okay. So that concludes the data taking for the lab and the analysis and whatnot. You should, of course, once you have these 2 voltage readings, you should predict as well what the voltage readings are supposed to be by using Ohm's law and by using Kirchhoff's laws. And so you should compare the theory value to the experimental value and determine whether the experiment matches the theory here for this step 4. Okay, so all told, what we've done over the course of this experiment is we've measured the resistance needed to put in series with the galvanometer for 3 volt full-scale deflection. 3 volts gives us 50 on the galvanometer, means 500 microamps. So you've measured that resistance, and you've measured the uncertainty in that resistance. And then in step 2, we put another resistor in parallel with the ammeter and found half-scale deflection. So that new resistor, the resistance of that new resistor, step 2, gives us the internal resistance of the galvanometer. In step 3, we changed the voltage to 8 volts. And we said, what is the new full-scale deflection? So in step 3, you repeated step 1, but now with 8 volts rather than 3 volts. So again, you should have an experimental value. You should have an uncertainty value. And what's new here is that you can use what you did in step 1 and in step 2 to determine what the answer should have been in step 3. And so you should compare the theory to the experiment for step 3. All right, and finally, step 4, we now took our voltmeter, which is set up for 8 volts full deflection, and we've only have resistance R1 and the galvanometer. We've removed resistor R2, and we've hooked up this voltmeter across first one and then the other of a pair of resistors that are in series, which have a total voltage drop of 8 volts between the two of them. And so here you should be measuring what is the actual voltage drop based on the voltmeter that we've built, set for full scale deflection 8 volts for the first resistor, and what is it for the second resistor, and then you should compare that to what the theory says using percent error, using Ohm's law, and using Kirchhoff's rules. So that does it for this lab. Hopefully you're able to work with this format, and good luck to everyone.